You know that math trick for checking if a number is divisible by 9, where you just add up all the digits? Well, you might think it's just a clever little shortcut, but it turns out these tricks are actually windows into a much, much bigger and more elegant system. These are rules that govern all numbers. So today, let's pull back the curtain and see the beautiful universal laws that are really running the show.
Okay, right off the bat, here's a question for you. Is 1,128 divisible by 6? I mean, you could grab a calculator, sure, or try to do the long division in your head, but it's not super obvious just by looking at it, is it?
Yeah, that one's a little tough. So let's back up and try an easier one to get warmed up.
What about this one, 7,389? Is that divisible by 9? Now for this one, you might just have a trick up your sleeve.
And there it is, the famous rule of nines. You just add up the digits, right? So 7 plus 3 plus 8 plus 9, that gives us 27. And is 27 divisible by 9? Yep, it's 3. So that means our original number, 7,389, is also perfectly divisible by 9. It kind of feels like magic.
But here's the real question. Why does that work? Is there something special about the number 9? Or is this part of some bigger pattern? You know, is it just a random one-off trick we all had to memorize in school?
Well, this research paper has the answer, and it turns out this isn't a random trick at all. Nope, it is a fundamental property of how our number system is built. And to really get it, we first have to talk about something called a number base.
So the system we all use every single day is called base 10. That's simply because we have 10 unique digits to work with, 0 through 9. But that's not the only way to do it. Computers, for instance, they use base 2, which only has 2 digits, 0 and 1.
And it turns out pretty much any whole number bigger than 1 can be a base. So we're really comfortable in our base 10 world. But base 2, or binary, is literally the language of all computers. And things like base 16 are used everywhere in programming. Our system isn't special. It's just the one we're used to.
And this is the big reveal. That rule of nines isn't really about the number 9 at all. It's actually the rule for whatever your number base is, -1.
Let's look at the official rule from the paper. It says, for any number in any base, we'll just call the base beta. If the sum of its digits can be divided by beta minus 1, then the original number is also divisible by beta minus 1. So, since we use base 10, our beta is 10. And beta minus 1, well, that's 9. That's why it works. It's not a trick. It's a law of mathematics.
And it gets even cooler. This rule for base -1 is just one of 3 incredibly simple, totally universal rules for checking divisibility that work in any number system you can imagine. Okay, here's the cheat sheet with all 3 keys. First, to test for the base itself, like 10 in our system, you just check if the last digit is 0. Super easy. The second one is for base -1, which we now know is our rule of nines. Just sum the digits. The third one is for base +1, which for us would be testing for divisibility by 11. For this one, you take the alternating sum of the digits. So you add the first, subtract the next, add the one after that, and so on. These 3 rules work for any base, anywhere. It's amazing.
Now, this isn't just a cool party trick for math nerds. These universal rules have really practical applications, especially in the world of computer science and programming. So the paper gives us a great little example. Let's take the number 3212, but let's say it's written in base 6. How could we possibly know if it's divisible by 2 or 3?
Well, we can use code. Modern programming languages, like Python, can actually understand numbers written in all sorts of different bases. You can literally just tell it, hey, this number is in base 6, and it gets it instantly.
And when the researchers in the paper run the code, it takes that base 6 number, translates it to our familiar base 10, tries to divide it by 3, and what do you know? The remainder is 0. It's a perfect match. The rules hold up.
So now that we see how numbers can be understood in any base, the paper explores another really powerful idea that builds right on top of this. If you can write numbers in different bases, could you use that to make them more efficient? And the answer is yes. It's called compressed representation. Here's how it works. You take a number in a small base, like this long one here in base 3. Then you group its digits into little blocks. Now the key is to pick a higher base that's a power of your current base. So, since base 9 is just 3 squared, we can group our digits into blocks of 2. Then you convert each of those little blocks to its base 9 value, and you end up with a much shorter number that represents the exact same value.
And of course, the researchers confirmed this with code. They took the long base 3 number and the short base 9 number, converted them both into our normal base 10, and they were identical. The value is perfectly preserved. It's an awesome way to make data storage way more efficient.
Okay, so we've gone through universal rules, different number bases, even compressing numbers. What's the big takeaway here? What's the point of all this?
Well, first, it shows that those simple math tricks we all learn are actually just the tip of the iceberg. They're windows into these deep, universal laws. Second, it shows just how beautifully consistent the rules of arithmetic are. It doesn't matter what number system you're using. Third, these aren't just ideas for a chalkboard, they have real, concrete uses in computing. And finally, it proves that numbers are flexible. You can rewrite them and represent them in different ways to make them more efficient.
The researchers sum it up perfectly in their conclusion. They say it's clear we can generalize these rules. They aren't quirks of our base 10 system. They're fundamental truths about numbers themselves, period.
And all this incredible insight comes from a paper on divisibility and number representation, published in the Agenda International Multidisciplinary Quarterly Research Journal.
It really makes you wonder, doesn't it? If a simple little trick for the number 9 is actually a universal law of mathematics, what other profound, beautiful patterns are hiding right there in plain sight, just waiting for us to see them?